All right. And we're underway again. So when I do post these up, it's going to be like 4 or 5 videos or however long. 10 videos, each half an hour long, right? All right, so let me reset it for the next round here. And start. And the countdown commences. Okay, so any more questions about that? Are you okay with that? Okay, any more questions about that? Yes?
How is that different from interstellar reddening?
Very different from interstellar reddening. Interstellar reddening is not spectral lines being emitted by ionized hydrogen recombining. Interstellar reddening is caused by dust particles. Remember that dust particles in the interstellar medium are better at scattering short wavelengths of light than they are long wavelengths of light. And so, as a result of that, if you have a bunch of light coming our way from a star, and there's dust clouds in between us and the star, then the idea is the dust particles in the cloud scatter more of the short wavelength photons than the long wavelength photons. To simplify, we're showing it as just red and blue. It's really photons of every color. A bigger fraction of the short wavelength photons get redirected out of the beam that was headed our way than of the long wavelength photons. So our star is starting out with a nice even mix of red and blue, but by the time the light reaches our telescope, obviously not to scale, by the time the light reaches our telescope, a much bigger fraction of the red photons have made it to us, the long wavelength photons, than the short wavelength photons. So the color of the star literally looks different. It looks redder because a bigger fraction of the long wavelength photons have made it through the dust and gotten to us than the short wavelength photons. That's a very, I'm sorry, go ahead.
That's one of the sunsets, right?
It is, except again, be careful. It's not because of interstellar reddening that the sunset is red. It's the same kind of physics, but it's a different cause in that it's not interstellar clouds between us and the sun. There aren't any interstellar clouds between us and the sun. It's the air in our atmosphere and dust particles in the air in our atmosphere that's causing it. So that's a totally local to Earth phenomenon. On the moon, sunsets are not different color. Sunrises and sunsets are no different color than when the sun is high in the sky, because the moon doesn't have any atmosphere. And so as a result, this doesn't happen on the moon. But it does on Earth, because we have a thick atmosphere. And we're looking for a longer length of atmosphere at sunset or sunrise than we are when the sun is high in the sky. Okay? What's next? Yes?
I want to know the age of the star cluster based off of its, the turning point.
The turn off.
The turn off point.
The turn off. How do we know the age of a star cluster from its turn off point? Okay. So, let me do that one up here. What chapter is that in again? The 10th, yeah, here it is. Okay. Yeah, it's chapter 15. Yeah, your book does it at a bit of a different point than many books do. So, many books discuss it in a different chapter than the near stars chapter. Okay, so, idea here is that how long a star spends on the main sequence depends on the mass of the star. Right? The more mass of a star, the less time it spends on the main sequence. Meanwhile, all the stars in a cluster are essentially the same age because clusters are litters of stars. In other words, when mama dog has a bunch of puppies, all those puppies are born at the same time essentially. They're all the same age. Clusters are litters of stars. A big cloud of gas fragments into many, many stars. And so they're brothers and sisters. They're all litter mates. They're all the same age essentially. And so if you imagine plotting an HR diagram of the cluster over time, what you'll find is as the cluster ages, more and more of the stars on the upper end of the main sequence turn into giants as time goes on. So for a very young cluster, you would find the entire main sequence was there. That's actually not quite right because the lowest mass stars only formed for a very, very young cluster. But at least the entire upper main sequence will be there for a very young cluster. But as the cluster ages, more and more of the high mass stars leave the main sequence because high mass stars don't spend as long in the main sequence. They burn through their fuel quicker. And computer models tell us how long stars of a given spectral type and associated mass spend on the main sequence. And so what we can do is we can look at the HR diagram for a cluster. We can figure out where the turnoff point is. In other words, where the uppermost part of the main sequence is, beyond which stars are leaving the main sequence. And if our computer models say stars of this spectral type spend so many years on the main sequence, that must be how old the cluster is. And that's what it comes down to. You figure out, if you know how long stars at the turnoff point spend on the main sequence, that is how old the cluster must be. Note that all of these stars are the same age, but these ones on the horizontal branch are more massive than the ones on the main sequence because they got to the horizontal branch quicker. They evolved more quickly. These guys on the red giant branch are more massive than the ones on the main sequence because they got to that stage of their evolution quicker. They're all the same age, but the more massive you are, the faster you go through your stages of evolution. And so that's the key there. Anybody want to ask more about that or for more clarification? Okay. Yes?
I know like the approximate maximum mass is like 150 and
Like for the mass of the star, as
Yeah.
massive as you can get is like,
Right.
yeah, we don't know exactly where the upper limit is, but
Right.
it's like 150, 200, something like that
Yeah.
times the mass of the sun. Yeah.
But what sets that limit?
What sets that limit is, remember there's this mass luminosity relation that says that the more massive a star is on the main sequence, it only works on the main sequence, the more massive a star on the main sequence is, the bigger its luminosity is.
Yeah.
And we already know that's the reason why more massive stars live shorter lives, because a star with 10 times the mass of the sun has about 10 times as much fuel to burn, but it's something like 3,000 times the luminosity of the sun. So even though it's got 10 times as much fuel, it's burning through it 3,000 times faster. That more than makes up for the fact that it's got more fuel to start with. Well, carrying that onwards, as you get to more and more massive stars, the luminosity gets bigger and bigger and bigger, much faster than the mass rises. If you get to like 150 times the mass of the sun, although we don't know exactly where the upper limit is, theoretical calculations say more like 80, 90 times the mass of the sun. So probably anything more massive than that is an unstable star. It's not going to stay that massive for very long. But the idea is, if you imagine keeping adding mass to the star, its luminosity eventually becomes so big that what we call radiation pressure in the outer layers, pressure due to photons, which carry momentum and push on things, radiation pressure in the outer layers becomes stronger than gravity, and so the star's own light will blow the outer layers off into space if it gets more than a certain mass. That's what's setting the upper limit, is the star's own light will blow the outer layers off because of radiation pressure once you get above a certain mass, because it has to be so luminous just to keep its core from collapsing with that kind of mass.
So is it just basically like impossible for it to be bigger than that, so this blows itself up?
It wouldn't explode, but in other words, suppose that you took, suppose you had this power, you had this really massive star, and you dumped 200 solar masses of material on it.
Okay.
Then it wouldn't explode. What would happen is the luminosity would rise so high that all that mass you added would be quickly blown off into space by really strong stellar winds.
Okay.
It would just poof its outer layers off into space in a, by stellar standards, very short time scale.
And that's what causes like all our elements to be here, right?
Not that per se, but when stars die, they return some, when a star dies, it returns some of the stuff that it built in its core into the interstellar medium. So a low mass star like the sun will eventually become, for example, a carbon star, where towards the end of its life, when it has a core that has carbon built from helium fusion, there are stages when it's an asymptotic giant branch star where convection reaches down into the core and stirs the core material up into the outer layers. And then, when helium shell flashes blow the outer layers off into space, that carbon gets returned to the interstellar medium. That's the primary source of interstellar dust grains. When a high mass star blows itself to shreds in a supernova explosion, it's returning material that it built during the explosion and before into the interstellar medium. And so over time, the interstellar medium has been enriched in heavy elements, including the stuff that our bodies are made of, that our Earth is made of. It all came from stars or colliding neutron stars or whatnot, various astrophysical phenomena involving stars or their remnants.
So going off that, like how, like, it talks about like the gold, silver, and platinum,
Mm-hmm.
like the other elements. I know like the top four, but how are those ones?
Yeah, so, all right, I'm going to do it. Told myself I wouldn't, but I'll play you the very end, because it's got a nice simulation of it here. Of some dude talking about the formation of the elements. So, let me skip to the end so I can tolerate it here. Oh, that sounds good, doesn't it? Okay.
Created when white dwarfs explode after mass transfer from a companion star, or maybe a collision with a companion white dwarf, causes the temperature to exceed the 600 million Celsius needed to fuse carbon.
This is for type
After
1
that happens,
explosion.
fusion of further elements occurs all the way up to the iron group. I think that it's absolutely amazing to realize that the iron in this weight and the iron in the hemoglobin that makes your blood red came from exploding white dwarfs billions of years ago. Thanks very much. Either way, mounting evidence,
That's where I wanted to be.
so
This
it's rigged, and stars at the end of their lives, for example, like, again, the star that made the Ring Nebula. But gold, like here in my rig, and platinum, and some other elements as well, need to be made in an environment that's much richer in neutrons. So it's actually, it turns out, not settled exactly where that happens. One possibility is in supernova explosions, but there's mounting evidence that the gold in the universe is mostly made by colliding neutron stars, boom, that collide with one another, and the neutron stars are super dense balls of neutrons that are left over when iron cores collapse. Either way, I think it's incredible to realize that
all things like that. The gold in my ring, blah, blah, blah. So colliding neutron stars, it turns out, there's that have the right conditions for the formation of gold by neutrons colliding with things like iron atoms in the outer crust of the neutron stars and so forth. So we think that precious metals and rare earth metals and so forth are mostly made in colliding neutron stars. Astronomers at Harvard studied a gamma ray burst due to a pair of colliding neutron stars and estimated that that single neutron star collision made a mass of gold equal to about the moon in gold. Which sounds like a lot, but neutron stars don't collide that often, and this stuff gets spread out into interstellar medium, so on the whole, still gold is still very rare. Platinum is very rare. Silver is very rare. But gold, silver, platinum all seem to be made by colliding neutron stars. Yes?
Well, like, iron mass stars, when they go through the process and there's more iron that's going to go up in itself.
Mm-hmm.
It's true that the iron cannot go through the nuclear fusion, so that's why
Right, so when a massive star builds up iron in its core, it's doomed because if you fuse anything with iron, you have to put energy in instead of getting energy out. So iron cannot serve as a nuclear fuel. So unlike before that point, where each time you build up the core with a new element in it, eventually the core gets hot enough to start fusing that element. That stops with iron because you can't get energy by fusing iron. So once the core builds iron through what's called silicon fusion, you're out of nuclear fuels. And eventually the iron white dwarf essentially is what it is. It's supported by electron degeneracy pressure. As the silicon fusion shell surrounding it keeps adding more mass to it, it eventually goes above the white dwarf limit of 1.4 solar masses. It can no longer support itself by electron degeneracy pressure. It collapses, and the energy that that releases is what causes the supernova explosion. Yes?
Can you talk about how the interiors of low mass and high mass stars are not well mixed, and then what that has to do with the existence?
Giants, yes. So, the reason why, if only I didn't have to talk. The reason why, this is awesome. Over the weekend, great. Then darn it, I have a job where I have to talk. But anyway, sugar-free. What's that?
Yeah.
Oh yeah, chapter, what is it, 17, I think, yeah. Right. So, this is showing the idea. So, for stars about the sun's mass, the reason why they're not well mixed is because the outer layers are convective and the core and outside the core is radiative. And so convection is how you stir things together. Convection is what would stir and mix a star, but most of the star is not experiencing convection. And in particular, the core is not experiencing convection in a star like the sun. And so that means that most of the stuff outside the core isn't getting stirred into it to serve as fresh fuel. So when the core runs out of fuel, there will still be fresh fuel surrounding it. And that, I'll get back to it, so that's why you can make giant stars. For high mass stars, it's flipped around. In high mass stars, it's the core that's convective, but surrounding the core, it's radiative. So it's still true that the material outside the core doesn't get down into the core. So it's kind of like those ads for Las Vegas. What happens in Vegas stays in Vegas. What happens in the core stays in the core, because convection is not stirring stuff from outer layers, from layers outside the core into the core. The exception is the lowest mass stars. The lowest mass stars are mixed all the way through. The lowest mass stars, for that reason, will never become giants. But other stars become giants because remember that once the core runs out of fuel, it starts to contract because there is no longer nuclear reactions going on inside the core. And so you're back into this situation like when it was a protostar, where gravity is stronger than pressure. As the core shrinks, then it's going to convert gravitational energy into thermal energy and heat up. And that ignites fresh fusion around the core in a shell of hydrogen surrounding the core. So of course, the reason why this lack of mixing allows stars to be giants is because it's what's responsible for shell burning. Remember, the giant stages of stars happen when shell burning is happening as opposed to core burning, is when stars swell up and become giants. Because shell burning is faster than core burning, because the shrinking core heats the shell up to a higher temperature than the core ever was when fusion was happening inside the core. So if that's the story, anybody want me to reiterate that or re-say that in a different way or anything like that? Yes?
For order for a star, it goes from
For the sun, you mean the order of the layers on the way inwards?
Yeah.
Yeah, corona is the outermost layer. We see that in X-rays. Then there's the chromosphere, which is, it looks pink. It's what you see in a solar eclipse. It looks like little pink leaks of flame. Those are part of the chromosphere. Moon. In a total eclipse. So you got chromosphere. Then what? Photosphere. That's the layer that we see with our eyes. And then once you're below the photosphere, if we slice through the sun, at some point I have a slicey thing like that. I don't remember if I have something that shows that. Your book does, but yeah. Anyway, once we go, good enough. Once we go below the photosphere, then we're in the convective zone, and then inside the convective zone is the radiative zone, and then inside the radiative zone, part of the radiative zone really is the core, where the reactions are taking place. That's for the sun. For other stars, there can be differences. For example, high mass stars don't have coronas. It turns out that they don't have strong magnetic fields. So high mass stars don't have coronas, they don't have chromospheres. They just got photospheres, and then a radiative zone, and then a convective core. And for the sun, it was the order that we just gave. Yeah.
And when it comes to energy, so before, in nuclear fusion, which generates the energy, to radiation.
So that's powering the whole thing. And then the radiative zone and the convective zone are both transporting energy outwards from the core towards the surface. Via radiation in the radiative zone, via convection in the convective zone.
Yeah, the radiation sort of bounces around.
Yeah, the radiation's kind of bouncing around, but because it gets hotter as you go in, there's always more energy going out than going in. There's always energy going in both directions, but the temperature goes up as you go toward the core. So in any given point within the sun, there's always more energy going out than going in, so there's a net outwards transport of energy as a result of that. Overall, there's more energy flowing towards the surface and towards the core. So the net flow is out towards the surface. It's kind of like if you had a train station, and for every 200 people that were walking towards the exit, 190 people were walking in towards the train. Overall, there'd be more people leaving the station than going into the station. Okay, I see 3 hands, and I'm just gonna, okay, so I'll just go row by row. So, yes?
The solar thermostat, is that just a balance between pressure and gravity and radiation and something else?
No, that's gravitation. So the balance between pressure and gravity is gravitational equilibrium. Gravitational equilibrium is the idea that at every layer within the sun, the pressure pushing outwards and the gravity pulling inwards are in balance with one another. Both increase as you go towards the center. Both I should say, well, actually that's okay. Yeah. Anyway, the idea is that as you get deeper in, the pressure increases because the weight of the overlying layers increases. And so at any given point within the sun, the outwards pressure is pushing up equal to the weight of all the overlying layers. That's gravitational equilibrium. Whereas, what you're talking about is the solar thermostat. That's a different piece. The solar thermostat is why the sun doesn't blow up like a bomb. That's this idea that if the sun, let's say that there was a slight rise in the temperature of the sun's core, then what would that do to the nuclear reaction rate? If it got hotter, would the nuclear reaction speed up, slow down, or stay the same? They'd speed up. That speed up would raise the pressure in the core. That energy released would raise the pressure in the core, make the core expand and cool back down again, and restore the original equilibrium situation. That's the solar thermostat. That if you increase the nuclear reaction rate, the natural reaction would be that the core would expand, cool down, and slow them back down again. As opposed to a situation where they went out of control. name a situation where they go out of control if you start nuclear reactions. Like in a white dwarf star, it's degenerate. If carbon fusion starts to happen, then it goes out of control, because if you have degeneracy, does the pressure rise when the temperature goes up as a result of nuclear reactions? For degeneracy pressure, does pressure depend on temperature? It does not, right? The degeneracy pressure doesn't depend on temperature. So when nuclear reactions start in a white dwarf as part of the binary star system, the release of energy raises the temperature, which makes the reactions go faster, but it can't expand and cool down because it's degenerate, and so it goes out of control. The reactions just go faster and faster and faster and blow the star to shreds. So if there's degeneracy pressure, you don't have a thermostat. It's not working, because the crucial part of the thermostat is if you raise the temperature, you raise the pressure, and it can expand and cool down.
Can you just briefly explain what neutronization?
Neutronization, yes. Neutronization, as the name kind of implies, means turning things into neutrons. And it happens in a star, in a massive star that is blowing itself up as a supernova. And so the idea is that when the star, when the core is collapsing, during the collapse of the core, electrons can combine with protons. And when you combine an electron with a proton, the result is a neutron and a neutrino. So neutronization is what turns the iron core into a neutron star. Electrons in the core combine with protons in the core, turn them into neutrons. That ball of neutrons is the neutron star. That's where the neutrons came from. The neutronization when the core is collapsing, the electrons combining with the protons.
Okay.
And that produces the burst of neutrinos that we saw from, for example, supernova 1987A. We saw a burst of neutrinos before we even saw the supernova, and that made us very confident that we know what we're talking about, because we had theoretically predicted there would be a burst of neutrinos. Without even knowing what it was, we saw a burst of neutrinos. A few hours later, hey, there's a supernova happening. It didn't take long to put two and two together and say, holy crap, we saw the neutrinos from the supernova, from the neutronization.
Okay. Thank you.
This is more of a general question. Will we need a calculator?
You shouldn't.
Okay.
No, if you like the last one, you shouldn't need a calculator. No.
Will there be even less math problems on this one?
I'm sorry, what?
Will there be even less math problems on this one? I just feel like there.
I haven't counted them, but I think probably yes, just because the other one had more opportunities for me to ask mathy kind of questions. But with this one, I can still, there's some stuff I can still ask you that's mathy, just probably not as much. Yes?
What do we learn
From observing the neutrinos?
or
From what?
from neutrinos?
Well, for the sun, for example, observing the neutrinos showed us that there weren't as many neutrinos coming from the sun as we expected. And eventually that led to the discovery that that the three different types of neutrinos can turn into one another, which is how we solved that problem. We realized that neutrinos from the sun are all, when they're created, they're all electron neutrinos, they're called, but they turn into the other two kinds of neutrinos. Some of them turn into the other kinds of neutrinos on the way to the Earth. So by the time they get to Earth, if the original neutrino detectors could only see electron-type neutrinos, and we were only seeing about a third as many as we expected. More recent detectors can see all three types of neutrinos. With them, we see as many as we expect. So that said, oh, they turned into the other kinds on the way here. All right, so one more starting to stop here.